In the last video, we had used the law of conservation of energy, which says that energy can neither be created nor destroyed, or in other words, the work done on any object is equal to the energy gained by that object. And we use that to come up with the formula for potential energy of an object. In this video, let us use the same law of conservation of energy to come up with the formula for the kinetic energy of an object. So let us start by taking a football here, and the mass of that football is m units, and let's say we accelerate. So let us apply some force, because we have to do some work on this object, some positive work on this football in order to give it some kinetic energy. And let's say I kick it with some force for some distance, and let's say or rather push it, not kick it, let's push it with some force. And I obviously, when we apply some force to some object, we get some acceleration, right? Because it's an external unbalanced force, so it must cause an acceleration. So let's say we get an acceleration of a units in this direction, and I push this object for a distance of s units, after which I stop applying the force, and due to inertia of motion it will continue to move in that direction with the velocity obtained at this point. So obviously here it is stationary, so it has zero initial velocity at this point, because I accelerated it. So at this point it will have some velocity v, and once I reach here and I stop applying the force, it will continue to travel with that constant velocity, which is v, and thus it will have some kinetic energy corresponding to that speed. So let us start by taking this formula: work done should equal the energy gained. And in this case, because we are not giving it any kinetic potential energy, we are not raising it by some height or doing anything of that sort, we are only giving it pure kinetic energy, or the energy of motion. So all the work that I give goes into increasing its velocity or giving it some kinetic energy. For now, let us ignore friction and assume that the surface is completely flat and smooth. So all the work that I do goes into increasing its kinetic energy, and hence work equals kinetic energy, or the work done on this object is equal to the kinetic energy gained by it. But obviously initially the kinetic energy is 0, so the kinetic energy gained is equal to the kinetic energy after I stop applying the force. Now I can simply write Ke on this side, just to get work on this side. Now work, right? Now what is work? Well, we know that work is the force applied multiplied by distance, right? So I can write this thing as force into distance, right? Now what is the force that I apply? Well, I know the ball has a mass of m units and it is being accelerated by a units. Okay, so we know by Newton's second law, force equals mass times acceleration. So we can use this equation, force equals mass times acceleration, to actually find the force that I need to exert on this to get this acceleration, right? So this means I am applying a force of m into ma units to accelerate it with this acceleration when the mass is m units. So let me just move ahead, and so I can write kinetic energy equals, well, instead of writing the force, I can write simply ma, or mass into acceleration, and that is being multiplied by d. So yeah, I have that expression. And what is the distance that I travel, that this object travels, due to while the force is being exerted? So the force is being exerted for this duration, during which the ball travels from this point to this point, and in this duration it travels a distance of s units. So instead of writing d, I can write that as s, because it is s units. So now what I get is Ke equals mass into acceleration into the distance. Now what I can do is I can use the equation of motion. So we had few equations of motion done in the first chapter, so let us use this equation of motion here. So the point here is I can use this equation to further simplify this here, And because here I have the kinetic energy in terms of mass, acceleration and distance. So let us simplify this further to get it into some more comfortable, into some variables that we are more comfortable to measure. So what we can do is, so here in this expression we know that for this particular case the initial velocity is 0. So because it is not moving at start, right? So we know u is 0, so u square also must be 0. So u square is 0, so this thing here becomes v square minus u square, or v square minus 0. So we have 0 there, or we don't need to write that 0 in fact, and we are left with 2as equals v square. So now 2as equals v square, and let's just shift this 2 on this side, and we get as acceleration to distance equals v square divided by 2. Now we can use this expression here, this equation, and we can substitute the value of, so we had mas, right, kinetic energy. Let me just remove this multiplication sign. So in essence we had kinetic energy equals m into a into s, mass into acceleration into distance, and we know that acceleration to distance, or as, equals v square by 2. So we can substitute this value here instead of this as, right, because as equals this thing obviously. So I can remove this part because that's as, and as equals this thing, so I can just put this instead of that. So let me just remove as from there, and instead of writing as there I can write v square upon 2. And here we are with the equation kinetic energy equals mass into velocity squared divided by 2. I can just extend that. So yeah, this is the same expression that we had come up with in the previous module. There I did not give you the reason why velocity was being squared, but in this derivation I hope now you can believe me that velocity should be squared, because we just that velocity squared came from the equation of motion. So yeah, now we know that kinetic energy equals mass into velocity squared upon 2, and it is only the velocity that is being squared, not mv. So it's only m into v square, right? So you have to square only the velocity, not both mass and velocity. And if both were to be squared, there would have been brackets, but because there are no brackets, only velocity is being squared. And that is the expression for kinetic energy, which we just derived using equation of motion, Newton's second law, and obviously the law of conservation of energy, and by which we know that the work done on any object, or rather the positive work done on any object, is equal to the energy that the object gains. And in this particular example, that energy was being gained in the form of kinetic energy. So that's it for this video, and I hope you've understood this, how we use the law of conservation of energy to come up with this formula. Yeah, and that's it.